Hello, my name is Micha Feigin-Almon, and I am with the Department of Mechanical Engineering and the Institute for Medical Engineering and Science at MIT. This talk looks at part of my work on using deep learning to bring seismic methods to real-time quantitative ultrasound imaging. I will be discussing the problem of looking at moving muscle and differentiating between motion and action, especially in the challenging case of dynamic scenarios. The goal is functional muscle imaging. That is, how to generate tissue-focused image maps that show physical values which directly correlate to muscle activation and relaxation. Muscles are designed with work in mind. Their job is to contract and produce force. This can be isotonic work, moving a limb through its range of motion, or isometric work, stabilizing a limb without moving. The teaser example shown here shows contraction of the soleus muscles. Denoted in red, the soleus is the internal of the two big muscles in the calf, and is located underneath the gastrocnemius muscle. The soleus and gastrocnemius are the two muscles tasked with performing plantar flexion, the extension of the foot. This is the motion we do when standing on tiptoes. The gastrocnemius is also in charge of bending the knee. So why is this a problem? The two ultrasound sign lobes here look at the biceps muscle in the arm. They show different ways of interacting with the external load of extending the arm. While the external action looks the same, the internal action is extremely different. There are three things that can happen when muscles contract. They can shorten, stay the same length, or lengthen. The left video shows an agonist-antagonist action. The two opposing muscles, the biceps and the triceps in this case, working in unison. Here, motion shows up as expansion in the Z direction. The right shows stretch-based control. In this case, we do not see the muscles, contraction-expansion action, and the left-right motion is mostly due to relative motion of the probe with respect to the arm. While it is true that based on external information regarding the action and load and some assumptions, we can guess that there is a contraction going on in the left image, it is impossible to tell if and how much active work versus passive motion is done and whether any actual action is taking place. The applications of this approach are numerous and far-reaching. In medicine, we are looking at neurological related diagnostics, such as muscle spasticity due to central nervous system conditions, muscle myopathy, and degenerative diseases such as Duchenne muscular dystrophy. Sports applications include techniques and training feedback, and assessment for return to play after injuries. We've also investigated questions of art. Can we learn to do better motion description and inference of action for motion? The proposed technology is the first step for developing wearable devices for in-home diagnostics and feedback, giving a more objective presentation than clinical visits. To date, there are no good ways of getting a cross-sectional muscle functional or health during motion. The first line of diagnostics is clinical examination, where the physician will perform palpation and work with the patient with or without resistance through the motion. This is subjective and requires experience and is not easy to isolate action. A dynamometer can help somewhat with the subjectiveness issue, but it is not easy to deploy either, and again gives a global image. The next option is EMG, but that measures nerve information, not muscle action. So addresses the neurological aspect directly, but only looks at the muscle aspect indirectly. It also provides global information in the case of surface EMG, or is too local and uncomfortable in the case of needle EMG. Finally, imaging solutions are currently only performed statically, with most of these not easily accessible in the clinic setting. With the partial caveat of ultrasound elastography, they focus on structure more than action, and all are done at rest, not in motion. Currently, the closest thing to the state of the art in the field is shear wave elastography. When muscles contract, they stiffen. The closest physical value related to our intuitive notion of stiffness is the Young's modulus. Shear wave elastography measures the shear modulus, a value that under assumptions that are almost true for soft tissue, is strongly correlated with the Young's modulus, and thus used to approximate it. This is done by generating mechanical shear waves. As shear waves are very slow compared to acoustic waves in the soft tissue scenario, their propagation speed can be measured using a stroboscopic-like approach with fast acoustic waves, the same waves used for classic beam-mode ultrasound imaging. While this approach has been shown to work for measuring muscle contractions with small fields of view in static scenarios, it is extremely sensitive to motion. The approach does not scale to dynamic scenarios. Just increasing the field of view or increasing physical resistance, thereby causing involuntary muscle shaking, is enough to prohibit any meaningful signal. This is shown in the images to the right, depicting the same experiment previously mentioned of inducing static contractions in the soleus and gastrocnemius muscles in the calf. Here, we tried replicating the shear wave elastography approach with a bigger field of view, at which point we failed to measure any action. The expected result would have been a green or red color at the top of the left image or at the bottom of the right image. As a surrogate, we switch our attention to speed of sound imaging. The speed of sound depends on the elastic Young's or shear modulus in a similar way to shear wave elastography. For better or worse, it also depends on the bulk modulus or spring constant, which is what makes the acoustic waves 2 orders of magnitude faster in tissue, in turn allowing for much higher frame rates. This not only enables functional muscle imaging in motion, but also tissue differentiation and improved image quality. Again, turning to the gastrocnemius and soleus example, here we see initial results measuring action. Red are high sound speeds correlated with contracted muscle. Green and blue is lower sound speed correlated with relaxed muscle. We see clearly the distinction between the activation of the soleus on the bottom in the left image and the gastrocnemius in the top in the right image. There is an added benefit mentioned briefly on a previous slide. The image formation model of the classic beam-mode ultrasound image assumes a fixed and known speed of sound. The signal is generated due to transitions between organs, which result in variations in speed of sound. This means that once we see an image, in practice it is incorrect. This variation not only causes a degradation in image quality, but also errors in physical measurements that are more limited in the longitudinal direction, but can go to around 30 or 40% in the transverse direction. So let us turn our attention now to experimental validation. We looked at differentiating the contraction between the gastrocnemius and the soleus muscle. These activate as a result of plantar flexion of the foot, that is, standing on tiptoes. Due to their physiology, the gastrocnemius takes most of the load when performing this with a straight leg, and the soleus with a bent leg. To this end, we look at subjects performing a squat maneuver, as demonstrated in the video. Here, we see the ultrasound probe attached to the calf, and the participant performing a squat maneuver, going from standing to squatting and back to a standing position. And here we see some results for healthy subjects, transitioning from a standing to a squatting position. It should be noted that this is a subset of the image set. Actual and theoretical frame rates are much higher. What we see here is a speed of sound map with red depicting high speed of sounds that we expect to correlate with contracted muscle, and blue with low speed of sounds that we expect to correlate with relaxed muscles. We can see the contraction of the gastrocnemius on the left at the top, and the contraction of the soleus on the right at the bottom. depicting the move through the entire motion, going from standing to a squatting position. Things get interesting when we look at a subject with spinal cord injury. The example shows a transition from squatting on the left to standing on the right. In this case, there is a severe degeneration of the soleus muscle, showing up also in the degradation of the B-mode image. On the left, we see an inconsistent activation of the soleus, transitioning to a mostly proper activation of the gastrocnemius on the right in the standing position. So let us shift our attention now to the question of how. The first step is to move down the signal line. The problem with using the B-mode image is that a lot of information has already been thrown out at this point. We go all the way down to the raw signal, the so-called channel data, where there is a lot of information hiding in the sign, phase, and structure of the signal. The problem is that classic inversion approaches suffer from several problems, making them inapplicable to single probe real-time imaging. They are slow, they require and are sensitive to initial guess of values, and they are unstable, usually requiring expert user interaction, which is inapplicable to the clinical setting. We choose to go with a deep learning approach. This is a data-driven approach. We need a large set of input signal and matching output speed of sound pairs to train a deep neural network to learn the mapping from input to the desired output. The problem is that there is no source of even small amounts of ground truth data, not to mention large data sets that can be used to train the system. To solve this, we turn to simulation-based training. We generated several thousand random sound speed maps consisting of random number of ellipses, of random dimensions and physical properties to simulate different organs and organ distributions, along with random speckle placed in the density domain, so as to not affect the wavefront due to numerical considerations. We then use numerical methods to simulate the ultrasound signal that would be generated by our specific ultrasound probe, looking at the given speed of sound maps. Finally, after getting all these generated speed of sound maps and resulting signals, we flip the roles. The network is shown the signals as input and the speed of sound maps as the anticipated output. And we expect the network to learn the mapping from the signal to the generating speed of sound map in order to recover speed of sounds later in real signals. So, to summarize the presented work, speed of sound maps carry diagnostic merit that not only matches shear wave imaging in places where it is used today, but excels in aspects such as function and action, tissue differentiation, frame rate, and resilience to motion. An interesting place where it can performs much better than shear wave elastography is in being able to differentiate fatty tissue from muscle tissue. High quality speed of sound maps can also lead in the future to improved imaging and the ability to correctly measure physical dimensions in the images. Deep learning, in turn, allows to achieve these goals in real time. While these are approximated measures, they can get pretty close to the actual results with interactive frame rates. Going forward, the next challenges are to improve transfer learning for better stability on real data, providing confidence values on the reconstruction in order to have an idea where we can better trust the resulting values and where they're not as trustworthy, and assessing the ability to recover other values from our data, such as attenuation maps and stiffness.